In this lecture, we are going to see when polynomials admit repeated roots. This is going to be useful when we construct finite fields. Before we do that, I would like to recall the derivative. So in calculus, you've all studied the derivative of a function, and a function is differentiable if a certain limit exists, and then you can compute its derivative. But we know that computing the derivative for polynomials is very easy. So at least the calculus theory of derivatives would work for polynomials with real coefficients because they would be functions of a real variable. However, even when you work over polynomials in any field, you can still make sense of the derivative formally. So let's take f to be any field. And then you have the space ft of all polynomials with coefficients in t, in f. And this has basis, it's an infinite dimensional vector space, and it has basis given by 1, t, t squared, t cubed, and so on. Now you define d from ft to ft to be the linear transformation. Well, to define a linear transformation, I just need to tell you what its values are on a basis such that d of t to the power n is n times t to the n minus 1 for all n greater than or equal to 0. Okay, so then this formally defined derivative is, there's no limit if you're working over, say, a finite field or over rational numbers. There's no clear notion of a limit. But this derivative does satisfy many of the same formal properties that ordinary derivatives satisfy. So then, for example, d of f plus g is df plus dg for all fg in ft. Right? That's just because we've defined it to be linear, so it's linear. But more interestingly, d of f times g is f times dg plus df times g for all fg in ft. I leave it as an exercise to prove this if you want to look at a detailed proof, but it's not difficult. It's just a formal proof, playing with symbols. Okay, now let's move on to our discussion of repeated roots. So firstly, the definition. Let ft be a polynomial in ft where f is some field, and then an element alpha that lies in E, where E is some field extension of f. So this notation here means that alpha lies in an extension of f, is called a repeated root if, of course, it should be a root, so that means that t minus alpha divides ft in the ring et, because t minus alpha, if alpha is in E, then t minus alpha is a polynomial in Et, and ft being a polynomial with coefficients in f, it's also a polynomial with coefficients in E. So t minus alpha should divide ft. That's just the property of being a root. Repeated root means that t minus alpha squared divides ft. Okay, so note firstly that in this definition, when I say repeated root, I do not insist that the root lie in the field over which the polynomial is defined. It could lie in a larger field. We've already seen that given any polynomial, we can always construct a field in which it can be written as a product of linear factors. So you could, for example, work in that field. Okay, so let's just look at an example. So last time we analyzed quite thoroughly the polynomial t to the power 8 minus 1 in Qt. This has no repeated roots. But the polynomial t to the power 4 plus 2t squared plus 1. Let's say this also in Qt has an element I in Q adjoin I over Q as a repeated root. In the Gaussian numbers, this ring Q adjoin I, the Gaussian numbers, the extension field Q adjoin I, we have a factorization of this polynomial as t plus I whole squared t minus I whole squared. After all, t plus I into t minus I is t squared plus 1, and this is manifestly the square of t squared plus 1. So the first polynomial has no repeated roots, whereas the second one has repeated roots. Okay, now let's come to the main theorem of this lecture. So let f be any field, and let's take a polynomial ft with coefficients in f. Then this has no repeated roots. So maybe I should clarify here, what does it mean for a polynomial to have no repeated roots? So let's just say that ft has no repeated roots if there does not exist any extension E over f and alpha belonging to E such that t minus alpha squared divides ft. So basically you're saying that repeated roots don't exist, just to be extra clear here. Has no repeated roots. So we want to decide whether or not a polynomial has repeated roots. And the answer is actually very simple. If and only if ft comma f prime t is equal to 1. So this is f, maybe I should write it as dft. I mean the derivative of f. So let me just recall, we discussed in Algebra 1 what these things are. The ring of polynomials, they form a principal ideal domain. Okay, in fact, they form a Euclidean domain. And since it's a principal ideal domain, if you take the ideal generated by ft and dft, that is going to be a principal ideal. So you would have ft and dft, this would be a principal ideal. And this could either be the whole ring or it could be something smaller. So by this I mean 1 in parentheses, or it could be, it would be generated by some, this should be dft. It would be generated by some polynomial gt. Okay, if that polynomial has degree greater than 1, then this is a proper subring of ft. And this polynomial gt, this is called the GCD of f and df. And we've seen in Euclidean domain, you can compute the GCD of two elements using by repeated application of Euclid's division algorithm with remainder. But for now, it's just enough to say that f has no repeated roots if and only if its GCD with its derivative is trivial. That means it has no common factors with its derivative. So that's the statement. And if you want, we can look at the examples. So if we go back to this example, let's take t to the power 8 minus 1. If this is ft, then f prime t or dft, the derivative of t is 8t to the power 7. Now these integers, we are working over Qt. These integers 8 and so on, these are just units in the ring, so we can ignore them. So what we have is t to the 8 minus 1 8t to the power 7. This is just the GCD of t to the 8 minus 1 and t to the power 7. Now any common factor of t to the 8 minus 1 and t to the power 7 must be a power of t, because it has to be a factor of t to the power 7, and the only factors of t to the power 7 are powers of t. But this thing has constant term 0, t to the 8 minus 1, so it's not divisible by any factor power of t. So these two polynomials generate the entire ring. And now let's look at the other example that we had. We have ft equals t to the power 4 plus 2t squared plus 1. Then dft is 4t squared plus 4t, which we can write as 4t cubed plus 4t, which we can write as 4 times t cubed t squared plus 1 times t. This polynomial is t squared plus 1 times whole squared. So what we have is that the GCD of ft and dft is actually t squared plus 1 in the polynomial ring Qt. And so you see, this polynomial actually has repeated roots, and the first polynomial t to the 8 minus 1 has no repeated roots, illustrating this theorem here. Okay, so let's move on to the proof of the theorem. Okay, so let's suppose that the GCD of f and its derivative is not 1. So suppose ft and dft, their GCD is generated by some polynomial qt, where degree of qt is greater than 1. So it's not a constant polynomial. Okay, so then take e to be an extension where qt has a root. Let's call that root alpha. Okay, we've already seen that such extensions exist. In fact, you can find an extension where qt is a product of linear factors. So then both ft and dft have a root alpha in e. So ft is equal to, so since qt is a factor of ft, ft also has a root alpha. So ft can be written as x minus alpha times gt. This implies that dft, now using the product rule for derivatives, this is x minus alpha times dgt plus just gt. Okay, but dft also has a factor qt which vanishes at alpha, therefore df alpha is equal to 0. But if I substitute here alpha minus alpha, that becomes 0, so I get g alpha, which implies that t minus alpha in fact divides gt, because g of alpha is 0. So together with this implies that f of t equals, so t minus alpha divides gt, so I can write gt as t minus alpha times ht for some polynomial belongs to, so all this here is happening, gt belongs to et in this extension, right? That's where this factorization is happening, because alpha itself is in et. So what we have is t minus alpha squared times ht in et, which implies that t minus alpha squared divides ft. So this proves the result in one direction, that if the GCD of a polynomial and its derivative is not 1, then the polynomial has a multiple root. Now let's prove the converse. So conversely, suppose we do have an extension E over F and an element alpha in E such that T minus alpha squared divides Ft in the polynomial ring Et. Okay, so in this theorem, this GCD is taken in Ft, but here we have this in Et. So let's just see what happens now. So what we have is f of t equals t minus alpha squared times gt. Now let's compute dft. So using the product rule for derivative, we get 2t minus alpha gt plus t minus alpha squared dgt. So t minus alpha divides both ft and gt, which means that the GCD of ft and dft is not equal to 1 in Et. This is the GCD in Et, but in this theorem, I don't want to worry about extensions. I just want to compute the GCD of ft and dft in ft. So, but the point is, it doesn't really matter. It turns out it doesn't matter. So here's a lemma. If ft, gt are two polynomials in ft, and E is an extension of f, and the GCD of ft and gt is rt for some polynomial r in Et. So in ft, let's say, so suppose the GCD of f and g is r in the ring of polynomials in the smaller field f, then I claim that the GCD of ft and gt is r even in the big ring of polynomials with entries in a larger ring. It's possible that you may, since you're allowing more polynomials, you may find more common factors between ft and gt. But what this lemma is saying, no, that this rt will generate the ideal of ft and gt even in Et. The proof of this is not very hard. It mostly just proceeds by thinking about what it means for these two ideals to be equal. So what we have is that we know that ft gt is equal to rt in Et, and we in ft in the smaller field, and we want to establish the same result in Et. So what does this mean? This is the same as saying that rt lies in the ideal generated by ft and gt. So this is equivalent to, maybe I'll just do one way. So this implies that rt is equal to atft plus bt gt for some at bt in ft. But ft is contained in Et, so that means that rt is at ft plus bt gt for some at and bt in Et. So this implies that the rt lies in the ideal generated by ft and gt in Et. which can be restated as saying that the ideal generated by RT is contained in the ideal generated by FT and GT in ET. Okay, and on the other hand, we also have that this implies that FT and GT belong to the ideal generated by RT. So FT is some QT times RT for some QT in FT, and GT is equal to ST times RT for some ST in FT. Now again, FT is contained in ET and FT is contained in ET. So what we have is that this implies that FT comma GT is contained in RT in also the larger polynomial ring ET. Okay, so putting these together, what we get is that FT GT is equal to RT in also the larger polynomial ring ET. Okay, so if the GCD of two polynomials is non-trivial in FT, it is non-trivial in ET. And that's all we need here. So if we go back, we showed that FT and DFT, maybe I should write it, DFT, their GCD is non-trivial in ET, but their GCD in ET is the same as their GCD in FT. And that's all we needed to prove. So the upshot is that a polynomial has no repeated roots if and only if its GCD with its derivative is 1. Let's look at this illustrated in the case of quadratic polynomials. Okay, so that's a very simple case, and it's also possible to work out the case for higher degrees. But let's ask, suppose we have a polynomial ft equals t squared plus at plus b. We could have taken at squared plus bt plus c, but it doesn't really matter because multiplication by scalars is scalars are units, so we can just take a monic polynomial belonging to ft. F is any field whatsoever. Now, in some extension, we have ft is t minus alpha into t minus beta. So alpha beta belongs to E. And ft has repeated roots if and only if alpha is equal to beta, has a repeated root if and only if alpha is equal to beta. So ft has a repeated root if and only if alpha is equal to beta, which can be written as if and only if alpha minus beta the whole squared is equal to 0. But this can be written as alpha squared minus 2 alpha beta plus beta squared. Now note that if we compare t minus alpha and t minus beta with t squared plus at plus b, what we get is that a is minus alpha minus beta and b is alpha beta. Using that, we can expand this in terms of a and b. This polynomial here is alpha squared plus beta squared plus 4 alpha beta, which is plus 2 alpha beta minus 4 alpha beta, and that is the same as a squared minus 4b. This is the discriminant. This is the, when we solve quadratic equations, we call this the discriminant. So a quadratic polynomial has repeated roots if and only if a squared minus 4b is equal to 0. So you can express the condition for having a repeated root in terms of the vanishing of a polynomial in the coefficients. Of course, you could have done this using the formula for the roots of a quadratic polynomial as well. But the nice thing of this method is that you can apply the same thing to higher degree polynomials. Suppose I had a cubic polynomial, t cubed plus at squared plus bt plus c. Then I can take delta to be the polynomial. Suppose this has roots, in some extension, t minus alpha, t minus beta, t minus gamma. Then I can take this polynomial alpha minus beta, beta minus gamma, gamma minus alpha whole squared. This is going to be a symmetric polynomial in the roots alpha, beta and gamma. It's going to be a degree 3 symmetric polynomial in the roots alpha, beta and gamma, and therefore it can be written as a polynomial in a, b and c. And this polynomial has repeated roots if and only if delta vanishes. Now you can try this at home. If you take this symmetric polynomial alpha minus beta, beta minus gamma, gamma minus alpha whole squared and express it in terms of a, b and c, you will get a polynomial expression in variables a, b and c whose vanishing will be equivalent to the cubic polynomial having repeated roots. So there is, I'm not deriving it, it takes a little more work to derive it, but there is a formula from which you can read off whether or not a cubic polynomial has a repeated root. And you can do the same thing with polynomials of any degree. There's always a discriminant from which you can read off whether or not it has a repeated root. So mostly in older books on the theory of equations, you will find these things computed in great detail. It's a lot of fun. So you can take a look at the internet or other references for the discriminant of a polynomial. We now come to a very surprising result about when irreducible polynomials have repeated roots. Theorem: if ft is a polynomial with coefficients in a field capital F is irreducible, then ft has repeated roots if and only if its derivative is identically 0. Very strange, you might say, right? How can a polynomial which is non-trivial have derivative 0? Well, okay, maybe it's constant and so it has derivative 0. But then that's not irreducible, that's a unit. So what are we really talking about here? Well, the example that we're really interested in is the polynomial like this. So suppose we have f is a field of characteristic p. So suppose f has characteristic p. This means that in f you start with 1, which definitely is the multiplicative unit of f. You take 1 plus 1, 1 plus 1 plus 1, and so on. So this generates monoid, and you can also take minus 1, minus 2, and so on. So this it could be either isomorphic to z, or it could be isomorphic as an abelian group to z mod pz, where p is a prime. So if you keep adding 1 to itself and you never get 0, then you say that the field has you would say infinite characteristic, but usually we say, for some perverse reason, we say the field has characteristic 0. So the rational numbers have characteristic 0, but suppose f has characteristic p greater than 0, where we mean p is a prime number, then f is an extension of the field z mod pz, where p is a prime number. So suppose f has characteristic p, that means that p is equal to 0 in f. That means if you take 1 and add it to itself p times, you get 0 in f. Then you can look at the polynomial ft equals a naught plus a1 t to the p plus a2 t to the power 2p plus an t to the power np. In short, we are looking at polynomials where the only powers of t that occur are powers that are multiples of p. Then you compute dft. Then a naught, well, its derivative is 0. a1t, it will be p times a1t to the p minus 1. This will be 2p a2t to the 2p minus 1, and so on, np an t to the np minus 1. But these p's are all equal to 0, so this is equal to 0. So here's your example of a polynomial which is non-zero, but its derivative is identically 0. So these are the polynomials in positive characteristic. In characteristic 0, you really cannot have this. If you have a polynomial which is of degree greater than 0 and its derivative is 0, then it has to be the 0 polynomial itself. So when the characteristic of the field is 0, we are saying that if a polynomial is irreducible, then it cannot have repeated roots. In positive characteristic, we are saying that if a polynomial is irreducible and it has repeated roots, then it must be a polynomial of this form where the only powers of t that occur are multiples of p. Okay, let's see how to prove this theorem. We'll just use the criterion for the existence of repeated roots that we showed a few minutes ago. So suppose f is irreducible. Then what can be the value of ft and dft? So then ft dft has to be generated by a factor of ft. So this has to be 1 or has to be ft. The only two possibilities, because only two factors of the only two divisors of the polynomial ft. So this has to be 1 or ft. Now, but this dft, the degree of dft is strictly less than the degree of ft. So you cannot have ft dividing dft because the degree of dft is smaller than the degree of ft, unless of course dft is identically 0. So this can only happen if dft is 0. In fact, if dft is 0, this is exactly what happens. The ideal generated by ft and 0 is the ideal generated by ft. And so that proves the theorem that a polynomial is irreducible, then it has repeated roots if and only if its derivative vanishes identically. And this is something which never happens in characteristic 0. So this is primarily of interest in positive characteristic. And this is where we are going to go next. We're going to construct finite fields, which are all fields of positive characteristic.